All right, good morning. So I am not a chemist, but I'm going to talk to you about some of the lightning research we've been doing lately that is relevant to atmospheric chemistry and in particular oxides of nitrogen, NO and NO2. This is really a lot of probably peeking under the hood of what's necessary to get a good estimate of NO and NO2 from thunderstorms and then apply that on regional or global climate modeling exercises and also air quality applications to figure out the balance between natural and anthropogenic contributions. And the logo you see here in the lower right corner is from the Deep Convective Clouds and Chemistry Field Campaign, which was a joint NSF, NASA, NOAA campaign in the summer of 2012. And we participated in that, and that's where the data for this talk come from. So let's first talk a little bit about LNOx production, transport, and photolysis in thunderstorms. LNOx is short for lightning NOx. NOx is active in ozone production, so it's relevant to greenhouse gas processes, and does so through photochemical reactions. There's a photochemical reaction pathway there. And lightning-produced NOx is actually the major natural uncertainty in the global NOx budget. Of course, the anthropogenic contribution is very, very significant as well, but in terms of natural effects, lightning is the major uncertainty there. And the vertical distribution of the lightning source is, and the resulting reaction rates, which depend on where that lightning winds up in the thunderstorm, is influenced by where that lightning originally takes place and then where the chemical constituents are transported. So here's an idealized picture of a thunderstorm taken from the DC3 science plan. You have the thunderstorm's updraft in the red lines here and the thunderstorm's downdraft in the blue lines. We have an extraordinarily idealized lightning bolt here in yellow. And of course, lightning might be producing NOx anywhere throughout this column, and then that's transported out into the anvil. And depending on where you're at in this upper portion of the cloud, the photolysis rate might be high, where there's plenty of sunlight, or in the lower part of this anvil cloud or deep inside of the thunderstorm, there'll be a low photolysis rate as all that light has been scattered away. So NOx is one of the chemical processes that were studied in this field campaign. There was everything under the sun, including lots of different organic chemistry that was studied with the aircraft in this field campaign as well. What's the uncertainty in the lightning NOx? I mentioned it was the major natural uncertainty, and it's about 3 orders of magnitude worth of uncertainty in terms of the amount of NO produced per flash or produced per channel length. And so you can see that, for instance, on this middle plot here, which is on a logarithmic scale, and there's 3 orders of magnitude and data points all throughout there. These estimates were made primarily from older lightning data sets, oftentimes just trying to use ground strike data and then correlating that to NOx production. And in order to do that, you have to assume a cloud and ground strike flash ratio to approximate how much is being produced inside the cloud. So there's a lot of assumptions made, and the reason the DC3 campaign was organized and eventually funded was because of the availability of better instrumentation to study both the in situ chemical processes as well as the thunderstorm processes, including much better lightning data than we've had in the past. So this is a schematic of the experimental setup. We have our thunderstorm with updraft and downdraft. 3 aircraft were involved: the NCAR Gulfstream 5, NASA's DC-8, and the DLR Falcon aircraft from Germany. They came over and joined us. There were environmental soundings, weather radars for understanding the mass flux through the storms by doing a dual Doppler wind retrieval. And then these lightning mapping arrays, which I'll tell you a little bit more about in a moment. There was also satellite data. There's an instrument called OMI that is able to retrieve with some degree of noise the NO produced using a remote sensing technique as well. And then there's also interesting stratosphere-troposphere exchange processes and mixing of ozone from the stratosphere into the troposphere as the thunderstorm penetrates through that interface. So lots going on. All right, so what are these lightning mapping arrays? This is the main instrument that I use for my research. We have in West Texas here a network of now 12 of these sensors that you see on the right side here. Essentially, it's just a radio receiver that happens to digitize noise pulses really, really fast. And it's solar powered, and these operate standalone. So let me walk you through how this detection process works. Because we have multiple stations, we're able to detect multiple, or we're able to geolocate the lightning process as it takes place. So you can imagine a little point along that lightning channel as the channel steps, and it's doing that very fast, 10 to the 6 meters per second or so. As it's doing that, a little radio pulse is emitted, and that's received by each of the lightning mapping stations. And by triangulating back to where that was, it's possible to triangulate back to where that was emitted. And you can do that for multiple points along the lightning channel. So we do this very, very quickly. We have a chance of a measurement every 80 microseconds. And so when you repeat that for an entire lightning flash, this is actually what the data look like when they come out of it. Color indicates time here, so the flash started with the blue dots, and then the channel progressed towards ground. You can see some branching there. And then later on in the flash, after the ground strike, there's some more processes that happen up inside the cloud. And so by locating this for every single flash for a thunderstorm, we can see how far a flash travels in the cloud. Here's another view of what the data look like. This is now a minute's worth of data, which I've sped up to 3 times real time. This is a complicated plot. The color indicates time, the most recent points in black, and then they fade out to white. And we've got a top-down view, so this is just like looking at a map here, and then a north-south projection and an east-west projection versus height. Next to that, you can imagine folding that up like a box, and then there's a time-height view on the top. So this is going to be an animation here, and this is what 1 minute of lightning data looks like. There's a real diversity in the size of these flashes and the way in which they fill space. There's a good big one. So this was from the June 6th, 2013 severe squall line that came through Lubbock. You might remember quite a bit of hail and severe winds with that storm. This is the leading edge of the bow echo right here, and lots of small flashes where the thunderstorm's deep convection is. And then in the anvil, some big flashes, and the trailing steady rain region, the stratiform region, there was more big flashes back there. Okay. So that's what we have. That's a lot more than a single point per flash, right? So how are we going to resolve this uncertainty in the LNOx production? Well, if we just correlate NOx measured by the aircraft to counts of lightning flashes and neglect, by doing that, we neglect the information contained in the flash size distribution. And so how are we going to do that? Well, we came up with this physical model of energy dissipated by a flash, and it's a very simple idea. We just treat the lightning flash as a capacitor, and for any capacitor, the area of the charged surface of that capacitor is proportional to energy. And so for a capacitor, you have 2 parallel plates, and they discharge, and so that's that area of the charged surface is proportional to the energy dissipated by the flash. We're going to define the flash size now is the square root of the area of the flash. How are we going to define the area? The area is the area of this blue polygon here, which is the 2D convex hull. It's a rubber band around the exterior points of the lightning flash. And we'll look at then statistics of this flash size distribution. And we can estimate the channel length from the area by assuming something about the nature of the branching, the fractal dimension of the flash itself. Okay, so here's data from one of the DC3 storms in Alabama, and there's 4 plots here. Flash rate in the upper left corner, in the lower left corner, the average size and standard deviation of flash sizes. In the upper right corner is an estimate of the total energy using this capacitor model. And then in the lower right here is both a 2-dimensional and a 3-dimensional estimate of the total channel length using that fractal-based approach. And so think about this statistically. There's, if you want the flash rate, that's the 0th moment of the flash size distribution. It's just a count. Energy is the 2nd moment of the flash size distribution. It depends on area, so that's the size squared. The length is a fractional moment of the size distribution, so that's a weird idea. It involves fractional integrals, so that'd be the 1.5 to 1.7th moment, depending on what you choose to be the fractional dimension. That's what that number is. And so it's instructive then to take all these different ways of measuring the lightning flash trends, and it looks like flash length, which we would expect to correlate to NOx production, right? More channel equals more NOx. That actually looks most similar to this total energy estimate. The flash rate and the total energy trends look quite a bit different. Okay, so a different way of looking at that. We can also distribute those channels in the vertical using the vertical locations of the lightning data. And you can see in these Alabama storms that fills space pretty evenly throughout the whole depth of the storm. We can do this for another storm in Colorado as well. Note again, the flash rate and energy trends are very different. And in these Colorado storms, what we find is that almost all the lightning activity is concentrated at 10 kilometers instead of distributed throughout that entire column. And so we now have this regional difference in where the NOx is being placed into the storm. And so not all thunderstorms are the same, and if we're going to account for this in a quality way in climate models, we have to account for that variability. Okay, so we use this very simple physical model of a flash, but that generated all of these different new quantities that we could compare with LNOx production, and that's enabled by a new instrument that is able to actually see more of the process, more of the lightning process. It's some ongoing work still to actually integrate the lightning and aircraft NOx observations in order to retune these LNOx parameterizations that are implemented in the different air quality models, chemical transport models. And this regional variation in the distribution of flashes in the vertical is actually due to some differences in the way the thunderstorm electrification processes work, the ice microphysics, and it's very sensitive to the thermodynamics. And we only understand that well enough to know that we should pay attention to it, and I have a PhD student working on trying to figure that out right now, what actually controls where and how the electrification happens. So that's all.
Questions? John?
Aaron, so with respect to climate, what would you project would be the response of thunderstorms to a warmer environment?
To a warmer environment.
Right.
Well, it depends. It depends on two things: whether or not you've warmed and added moisture, or whether or not you've warmed and dried it out. So, if you're warming and adding moisture, then you would expect more thunderstorms in a situation like that. Drying it out, it would tend to reduce.
So part of my question has to do with the difference in the data between Colorado and what was shown saying for Alabama. Is part of that due to the moisture availability in the cloud formation?
Yeah, that's right. So the electrification process is controlled by the availability of supercooled water in the mixed phase region of the storm, so ice and supercooled water together. And in storms in subtropical, very moist environments like Alabama, lots of liquid water is depleted by what are called warm rain processes, so lots of the rain falls out at low levels. We have very high cloud bases in the drier environments in Colorado, and so that reserves more of that moisture to the upper portion of the cloud. Right.
In the animation, you saw that looking north and looking south. Does that mean looking at the north direction or the plans?
When I said looking north, that's imagine yourself standing there and looking to the north, and so it would look like what the horizon looks like. Mm-hmm.
The thing about Colorado is that there's a big difference in times in terms of environments, right? So you have the grasslands and you have the mountains, and your data comes from where?
Right. So this is in the east of the mountains, away from the foothills, basically on the high plains. That's right. So these conditions extend all the way into northwest Kansas, and we actually get sort of a mixture of these kinds of storms and typical tropical convection in the Lubbock area. So it's an interesting place to work.
Great. Thank you.
Thank you.